Welcome everybody to this MOS Mathematics online seminar series. Jelena and I are very happy to be here today. So I'm just going to introduce a bit which these seminars consist of. So there are presentations from leading young academics in mathematics from around the globe, and the idea is that they give presentations that the topic obviously is mathematics, but they are accessible to a broad audience no matter the fields in mathematics we are dealing with. So this happened to when we were discussing from EMIA, because this is organized by EMIA, the European Mathematics Society Young Academy, when we were thinking of ways of giving benefits to young mathematicians. So we thought that this kind of talks were interesting for those who are working towards or have just completed a PhD in mathematics. We will have a talk every first Thursday of each month, and it will take 45 minutes long, and then we will have 15 minutes for questions. So if you want to stay tuned, you can register to this link, and we will update, we will send you the latest updates on the seminars. We will remind you the talks and also the links for our YouTube channel, because we will be recording these talks. So this is the schedule of the first season of MOS. And well, this bunch of people are researchers that have been awarded in the last European Congress of Mathematics. So as I said, from EMIA, we are organizing, Jelena and myself, and I think it's time to give the voice to Jelena to introduce our first speaker. Thank you.
Hi, everyone. Thank you for joining us. I will tell you a bit more about Cristiana, whose CV is quite impressive. She was born in Bari in Italy, and now she's an associate professor at the University of Parma in Italy. Cristiana's research is mainly devoted to problems from regularity theory in elliptic and parabolic partial differential equations, with special emphasis on those coming from the calculus of variations. She completed her PhD from the University of Oxford in 2019. In the same year, she was awarded a G-Research PhD prize. A year later, she was awarded with Gioacchino Iapicino Prize in Mathematical Analysis, and in 2023 with Bartolozzi Prize, and with International Prize for Mediterranean Culture. In 2024, she was awarded an EMS Prize given for her outstanding contributions to elliptic regularity. In 2023, she was elected for European Mathematical Society Young Academy. Also, in 2023, Italian edition of Forbes included her in the list of top 100 successful Italian women. She has more than 30 scientific papers, and she gave more than 90 invited talks. There is still a lot to say, but I think you're more interested in what Cristiana will talk about. You can ask Cristiana questions during the lecture or after the lecture. How do you want? So Cristiana, please, and thank you.
Many thanks for your very generous introduction. Let me try to share my screen. Now, can you confirm that you see my slides?
I cannot see it.
No. So entire screen. Okay, share. Now you can. Right?
Yes, now I can see it.
Okay.
Great.
So the first step is made. Now, again, thanks for your introduction. And what I'm going to talk about is some recent advances on the regularity theory for non-autonomous, non-uniformly elliptic problems. Of course, I'm going to talk about Schauder estimates. Precisely, I'm going to cover both variational integrals and elliptic equations, and the catch lies in the Euler-Lagrange equation that holds for minima of functionals. Okay, so what I'm going to present will apply to both functionals and equations. In the beginning, I said lots of non-uniformly, non-autonomous, so what am I talking about? Let me consider the most basic simple case of a linear equation with a metric coefficient. Let's say that mu is symmetric for simplicity. Now, this object is said to be uniformly elliptic whenever the ratio between the highest eigenvalue of mu over the lowest eigenvalue of mu stays uniformly bounded. If you can find just one point which this blows up, then we said that the equation is non-uniformly elliptic. Now, those are very basic notions that are related to the matter of regularity, above all at the gradient level. Now, imagine that I want to bring this machinery in the nonlinear setting. So I have an elliptic equation of the form minus divergence of A of du equals 0. A is nonlinear. So at least on a formal level, I can differentiate the equation so that each derivative of u, that now I call v, solves something that looks like a linear equation where now the metric coefficient is actually a nonlinear measurable function of the gradient. Then I simply recall whatever I used in the linear setting and I adapt it to the nonlinear one. More precisely, I look at the lowest eigenvalue of the derivative in the gradient variable of A and its highest eigenvalue, that are G1 and G2, that are two non-negative functions, and therefore I can characterize ellipticity by means of those two quantities. Recalling that the catch between equations and functionals lies in the validity of the Euler-Lagrange equation, if I want to transpose this notion to functionals, then I just want to look at the lowest and the highest eigenvalue of the Hessian of f. Okay? Now, I want to talk about uniform ellipticity versus non-uniform ellipticity. Then I have to look at the ratio between G2 and G1. Since I'm going to be interested in non-autonomous problems, of course, G2 and G1 can fairly depend on x, and therefore I would say that my problem is uniformly elliptic whenever this ratio stays uniformly bounded. Otherwise, I will say that it is non-uniformly elliptic. Now, the matter of non-uniform ellipticity is a very classical topic in the literature. There are, let's say, several important contributions before the 70s. You can recognize several heroes of the analysis of PDEs in this slide, but also after the 80s, there are several important contributions. Let me highlight in particular the work of Zhikov, who was a Russian genius who introduced several significant models, although being essentially uniformly elliptic, and the rate of non-uniformity came only from some misbehaving coefficient. Still, he laid down those model examples that gave lots of insights towards the general theory. Moreover, Marcellini gave also fundamental contribution as he laid down the foundation of the modern variational approach that is essentially at the basics of whatever we do right now. Okay. Now, as I said, why the variational approach is so crucial when dealing with this class of problems, and in particular if you're after sharp results. Well, first of all, it is let's say, the most convenient setting because it preserves the full energy information that comes simply by minimality, okay? So let me consider a functional that is non-uniformly elliptic in the sense that the ellipticity ratio related to the integrand blows up. Now, the most common rate of blow up you can find in the literature is the polynomial one, meaning that your ellipticity ratio blows up as a positive power of the gradient variable. Now, if you want to relate the rate of blow up of the ellipticity ratio to the growth ellipticity features of your integrand, what you can do is to prescribe the ellipticity in this form, in the sense that, thinking to the echelon, of course, in terms of matrix, you are saying that the echelon of F is trapped between two different powers of the gradient variable that multiply the identity. This way, you not only have a, let's say, a quantitative formulation of the growth ellipticity of your integrand, but also you relate it to the rate of blow up of the ellipticity ratio. Now, if one wants to make some sort of bet, one could say, okay, if the ellipticity ratio blows up too fast, maybe it can be problematic. Maybe there is no regularity. Maybe I need to choose P and Q quite close to each other to ensure regularity. This is actually not a bet. This is actually not technical, but it is a necessary and sufficient condition for regularity already in the autonomous setting. You need to pick your growth ellipticity exponent very close to each other in order to have reasonable regularity results. Otherwise, counterexamples are there that tell you that your minimizer might be unbounded. So no gradient regularity might be available. And those are classical results due to Marcellini and Giaquinta. Next, what happens if we plug in coefficients? This is the natural guess, right? And one could also imagine that the situation with a coefficient might be correspondingly more complicated, in the sense that if already in the autonomous case, something striking happens, in the sense that I can have a strictly convex integrand, smooth, the best that you have, that is non-uniformly elliptic, then regularity might fail, okay? If the rate of non-uniformity is too sharp, is too fast. So what happens if I plug in coefficient? Natural question, do I have any reasonable sort of Schauder theory? Well, quick crash course about Schauder estimates. We know that harmonic maps are smooth, right? This is super classical theory. So natural question if I plug in coefficient, let's say a matrix coefficient mu, that is bounded and elliptic. Now, since mu and u stick together, what I would expect is that if mu is either continuous, then the gradient of solutions is correspondingly either continuous. This is for every alpha strictly between 0 and 1. Now, this is a classical result that dates back to the beginning of the 30s of the previous century with the breakthrough results of Hopf, Caccioppoli, and Schauder, and there are also some contributions by Giraud. And what is important here is that all these results heavily rely on heavy potential theory. So they were very challenging and very technically involved. There are parabolic analogs, there are fully nonlinear analogs, non-divergence analogs, and this is a very basic tool in the regularity theory in the calculus of variations, because it is a totally natural question studying studying the influence of external ingredients in an equation. Now, later on, this original approach that goes via nonlinear potential theory, was streamlined by Campanato, Trudinger, and Leon Simon, and each of them essentially used the fact that having a quantitative decay information on the oscillation of coefficients, right, which is Elder continuity, allows to, let's say, quantify the closeness of your original solution to its lifting. That is the solution to the corresponding frozen problem. Okay, you're freezing the coefficient in one point. And thanks to the quantitative decay of the modulus of continuity of coefficients, you can place those two maps close to each other. And then essentially transfer regularity from the solution of the frozen problem to your original solution. Now, this is an indirect proof. It can be alla Campanato via the use of Campanato spaces, using the approach of Trudinger via convolution techniques, or via blow-up alla Leon Simon. But in any case, the cornerstone is the possibility of getting close to a very regular maps that features homogeneous reference estimate, excess decay estimates, and then simply extract the regularity from the frozen problem. The very same circle of ideas lies is at in the background of Schauder theory for quasi-linear elliptic equations. Let's think, for instance, to the non-autonomous P Laplacian. Okay, C is a coefficient that is either continuous, bounded away from zero, and either continuous. The P Laplacian is, of course, uniformly elliptic, and therefore we can use the same comparison argument in order to prove that the gradient of solutions is either continuous. The very same approach applies to general equations that satisfy so-called Radzyńska and Duracevas condition. So let's say that Schauder theory is very well understood in the uniformly elliptic setting, okay? And this, again, the key is the possibility of extracting regularity from a very regular problem without coefficient. Now, let's see what happens when a very mild rate of non-uniformity is available. This is the case of so-called Giaquinta functional, nowadays known as double phase functional, was introduced by Giaquinta in the setting of homogenization and to study the possible occurrence of Lavrentiev phenomenon. Now, this is a very elegant energy in the sense that it is the sum of a P Laplacian plus weight Q Laplacian. A is non-negative, but careful, it is allowed to vanish. Point by point, this is uniformly elliptic. However, since the coefficient has not enough positivity to rebalance oscillations around the point, the only way to trap this energy between a power of the gradient variable is to consider two different powers. So this lack of positivity, of strict positivity of the coefficient gives rise to a very weak notion of non-uniformity. But what is, let's say, interesting is that this model highlights, let's say, points towards the direction of sharp results in the strong non-uniformly elliptic setting. So towards the real Schauder theory for non-uniformly elliptic problems. This is a very beautiful counterexample due to Fonseca Mingione that relies on early construction of Jacobs that essentially tells you that, okay, take this double phase functional, consider a differential problem with a smooth boundary datum posed on a ball, so the best domain you could think about. Let us assume that P and Q are quite far apart from each other in a precise quantitative way that I will show you in a second. Then what happens is that this Dirichlet problem admits a solution, of course, whose singular set is a fractal, contains a fractal of Cantor type, and in particular, this makes this set of essential discontinuity points very large, okay? In particular, its Hausdorff dimension is almost maximal, in the sense that it is almost n minus p. Of course, this is a W1P map, so it cannot exceed n minus p. This means that your minimizer is not better than any of his competitors, right? Because it does not belong to any better space than W1P. It might belong to W1P plus epsilon, but not more. In particular, Schauder theory dramatically fails. While this counterexample is important, is that it is in sharp contrast with the uniformly elliptic literature, in the sense that this holds in the scalar setting, while in the uniformly elliptic case, to see the emergence of singularity, you want to go to the vectorial setting and then play with the anisotropy. Here, your problem is perfectly scalar. Moreover, your integral has radial structure, in the sense that it is defined upon the modulus of the gradient. This can be made non-degenerate, no problems. The domain here is a ball, so no singularity originates from some weird cusp in the boundary. The boundary datum is Lipschitz regular, so everything is perfect. Now, the real, let's say, origin of singularity is the pathological interaction between coefficient and gradient variable. Okay? In some sense, the coefficient hides some disturbing discontinuity in certain admissible competitors that are admissible precisely because the coefficient vanishes. Now, this counterexample has been perfected later on by Balchi, Dinning, and Surnachev, who essentially produced a minimizer with maximal Hausdorff dimension of the singular set later on. But this is already, in this case, it's already pretty clear that Schauder theory in the non-uniformly elliptic setting might yield surprises, okay? In particular, as we already saw in the autonomous setting, it cannot be true for arbitrary choices of P and Q. Now, the condition that is violated in these counterexamples is this one, okay? So keep it in mind as it will turn back. Concerning the regularity for double-phase integrals, this was achieved by Baroni, Colombo, and Mingione, but the fact that the double-phase energy is pointwise uniformly elliptic still allows for a perturbative approach, which has been later on extended to a rather large class of uniformly elliptic problems that in any case satisfy non-standard growth conditions, okay? However, the key point, both for the double phase and for all general class of uniformly elliptic problem, is that the frozen integrand is uniformly elliptic, in a sense that whenever I fix the coefficient in one point, then I have a perfectly bounded ellipticity ratio, and this ensures me that I can still get close to a lifting that is a minimizer of a uniformly elliptic energy, which has perfectly homogeneous excess decay estimates, and therefore I can still extract regularity from it. Now, if I try to use a similar circle of ideas in a very simple, genuinely non-uniformly elliptic model that is just C of x times f of dw, where f is non-uniformly elliptic, well, what I see is that, I mean, this approach simply fails because also for the frozen problem, the ellipticity ratio is uniformly bounded. The problem is non-uniformly elliptic, and therefore any sort of perturbative approach drastically fails. Now, so far we spotted the class. Please? Sorry? Can I go on? Is it a question? Okay. So far we spotted a classical fact that is for uniformly elliptic problem, Schauder theory holds, meaning that to an elder continuous coefficient correspond an elder continuous gradient, which immediately gives rise to an open problem. Can I see the same on non-uniformly elliptic problems? Let's say PQ non-uniformity. Can I say that if C is elder continuous, then the gradient is correspondingly elder continuous? This is a classical problem, and it was raised at several stages in the literature. For instance, this is a comment due to Gary Lieberman on the paper of Giaquinta Giusti, the one on Krell in 1984. He said that Giaquinta Giusti's freeze and perturb technique perfectly works in the uniformly elliptic setting, but drastically fails in the non-uniformly elliptic one, unless gradient boundedness, uniform gradient boundedness is available, which it was not. Therefore, here it is perfectly highlighted the failure of perturbative methods in non-uniformly elliptic problems. The same is the same issue appears in this important theorem of Ladizhenskaya and Duraltseva. Here, as you can see, they need to consider uniformly bounded gradients for solution. Then they need to impose heavy differentiability assumptions on all the entries or their nonlinear tensor. And in this way, they can derive Schauder estimates. Let me point out what Ivanov commented about this theorem. Also, Ivanov spotted what was the missing step towards a reasonable Schauder theory, and it was a big missing step. That is the lack of uniform Lipschitz bounds for solutions. Okay, this was the main difficulty. Indeed, once achieved gradient boundedness, then the non-uniformity of the problem becomes immaterial, because we saw that for non-uniformly elliptic problems, what characterizes non-uniformly elliptic problems is the blow up of the ellipticity ratio. But now, if the gradient is bounded, the ellipticity ratio has nowhere to blow up. And therefore, once achieved gradient boundedness, then the problem can be, in a sense, trace it back or put it closer to uniformly elliptic problems, and the theory becomes relatively more standard. Same observation has been made by Giaquinta and Giusti. Okay, now, an answer to this problem has been provided by myself and Mingione in the case for large class of non-uniformly elliptic problems, who were the ones about PQ non-uniformity. And we're also able to cover some anisotropic mu-elliptic problems. And let me highlight that, let's say, an important detail of discrepancy, an important aspect of discrepancy in our theory with respect to previous literature is that we offer a direct approach to gradient boundedness. Okay, indeed, since the early 30s of the previous century, the only way to achieve gradient boundedness in non-autonomous problems, the uniformly elliptic case, was to first prove gradient Elder continuity, okay, then retain gradient boundedness, and then push it, in case the operator allowed, to improve to improve to the highest level the Elder continuity exponent. So as much as your operator allows. Now, moreover, our approach is direct. Okay, since the problem is non-uniformly elliptic, we can no longer freeze and perturb and then extract regularity. The map that now iterates and produces regularity is your original minimizer, or let's say a regularized version of it. Okay, so our approach is direct, no longer perturbative. I will try to give you an idea of these results in a model case, but of course we can treat the more general one by relaxation. Okay, now in the model case C of x f of dv, where f is PQ non-uniformly elliptic and C is bounded away from 1 and Elder continuous, bounded away from 0 and Elder continuous, under the sharp bound that already characterized pointwise uniformly elliptic problems, we can prove that the gradient is locally Elder continuous in omega. Moreover, in the case of a non-degenerate or non-singular problem, we can recover the classical Schauder implication that tells you that if the coefficient is C0 alpha, then solutions are correspondingly C1 alpha for the same Elder exponent, of course, as long as alpha stays between 0 and 1. Okay. Okay, in the remaining minutes, I will try to give you an idea on how the proof works and what are the main aspects of the proof to highlight. Okay, let's say that the proof goes in 2 moments. First of all, we prove that solutions belong to all Sobolev spaces thanks to a fractional version of Moser iteration. Now, what is the problem here in using, let's say, classical Moser iteration, maybe the unbalanced one alla Marcellini? Well, first of all, to apply classical Moser iteration, we need to achieve the second variation of our functional, okay? Meaning, we need to differentiate the Euler-Lagrange equation. And here you can see the very first obstruction to this to regularity that lies in the lack of differentiability of coefficients. Coefficients now are Elder continuous, therefore Therefore, the Euler-Lagrange equation exists with no problems. However, it cannot be differentiated in the classical sense because, I mean, we do not have the full derivative of an Elder continuous function. Okay? The idea now, which is the key tool to handle this class of problems, is to read the Elder continuity as fractional differentiability, and therefore observe that our problem is not twice differentiable, but 1 plus alpha times differentiable, and this allows us to apply a fractional version of Moser iteration. Okay? Now, what happens in this fractional version of Moser iteration is that we can improve at each step the integrability of the gradient of minimizer as much as we like. However, we cannot reach L infinity precisely because the gain in integrability is linear rather than geometric. Okay? This means that we cannot achieve gradient boundedness, but still it is enough to place our gradient in all Lebesgue spaces, all finite Lebesgue spaces. And this is the very first step in the proof. Second one is a direct proof of gradient boundedness via fractional and nonlinear potential theoretic version of the George iteration that is then combined with a Bernstein type approach. So how does it go? Now, this in a sense is the more delicate and yet more innovative part of our proof, as it strictly relies on a fractional Caccioppoli type inequality that now is based on a localized in space version of Littlewood-Paley decomposition. And this is the very first ingredient. Second one is the use of a general class of nonlinear potentials. Here you see some, let's say, anonymous parameters, sigma and theta, but precise choices give you back the classical Avin-Mazia-Wolf and Riesz potentials that you can see. I mean, they have been historically applied in when studies find properties of solutions to, for instance, non-homogeneous equations with rough ingredients. For instance, measure data problems. There you can see some applications of these nonlinear potentials. Here, as we will see, we shall use those nonlinear potentials as carrier of information, of size information along iterations. I will be more precise. Okay, we said we use Bernstein. What is Bernstein method in the classical uniformly elliptic autonomous case? Well, it consists in showing that a convex function of the modulus of the gradient turns out to be a subsolution of a linear elliptic equation that is actually obtained by differentiating the original one. If you remember, this is the same argument that I used to move the information about uniform ellipticity and non-uniform ellipticity from linear equation to nonlinear one. Indeed, as soon as I differentiate the equations minus divergence of A of du equals 0, what I get is a linear equation with a matrix coefficient that now, if you remember, is a nonlinear measurable function of the gradient. This is the cornerstone of classical Uraltseva-Uhlenbeck theory for the P-Laplacian. Okay? Now, once I prove that modulus of the u to some power, say to the gamma, is of course a non-negative subsolution of a linear equation with measurable ingredient, then classical De Giorgi theory kicks in and allows me to conclude that the gradient is locally bounded. How do I prove that the gradient is locally bounded in the classical setting? Well, I show that it belongs, that my modulus of the u to the gamma belongs to a certain De Giorgi class, which is this one. This is the upper De Giorgi class. The availability of this inequality allows me to start iterations. This is perfectly homogeneous. Therefore, I can iterate and I can prove that the gradient is bounded. Now, what goes wrong for my problem? Well, as I said, to derive this inequality, what I did need was to differentiate my original equation. This perfectly works in the nonlinear uniformly, in the autonomous uniformly elliptic setting. However, it immediately fails as soon as an elder coefficient appears here, which makes no longer differentiable my equation. So it is the same problem that I mentioned before. Okay, how do I overcome this issue? Well, first of all, I prove again that a suitable convex function of the gradient, which you could think about like modulus of the u to the p, satisfies a class of renormalized Caccioppoli type inequalities on level sets that reads in this way. Okay, now you can see several characters appearing in this inequality. Well, on the left-hand side, you have a fractional semi-norm of a truncation of V, which, let's say, is in the spirit of a fractional De Giorgi type inequality on level sets. However, here you can see other components, okay? First of all, the blue part is a renormalization constant that accounts for the non-uniformity of the problem, while the red part reminds you the presence of coefficients, and indeed is there because coefficients appear. Now, who is H? H is a power type function, okay? And let me highlight that it is really responsible. It really accounts for the non-uniformity of the problem, because as soon as Q is equal P, meaning that your problem is uniformly elliptic, H simply disappears. Okay. Now, looking to the literature, you can see several forms of Caccioppoli type inequality. We have the classical one, which is the one that is obtained, as I described you before, by differentiating the problem. This is what you have when no coefficient appears. Moreover, again, in the literature, we can find a non-local uniformly elliptic Caccioppoli inequality, again, without coefficients. What happens now is that you're placing your truncation in a suitable fractional Sobolev spaces. In other words, you are controlling a fractional Sobolev semi-norm of V. And what happens now is instead the availability of a non-local, non-uniformly elliptic Caccioppoli inequality with renormalization. So what does it mean? We have to control a fractional Sobolev semi-norm of your truncation because we cannot fully differentiate the problem because of the availability of coefficients. Moreover, a renormalization constant appears here, the part in blue, that reflects the non-uniformity of our problem. And then we have the red block, okay, that is there because of the coefficient. Now, one could wonder why these renormalization constants appear. I mean, what's the point in having some power type function of a quantity that is essentially proportional to the L infinity norm of the gradient? I mean, it looks like a bit counterintuitive if what you want to prove in the end is gradient boundedness. Well, the presence of these constants is due to the fact that you want to somehow trick the problem, okay? To make this inequality look perfectly homogeneous. Indeed, homogeneity is the key point in order to make iteration work, okay? Moreover, the red part, which will eventually give rise to nonlinear potential, are used in some sense to carry size information, integrability information of the gradient along iterations. Okay, so to summarize, all this work is essential. Please tell me.
Ma'am, could you please explain the subscript symbol plus in first equation.
Oh,
Local
yes, yes. Plus means this is upper truncation. It means that you're taking the positive part of v minus k. This is the maximum between v minus k and 0.
You mean
Okay.
Heaviside function, unit step function here?
No, this is just you're essentially taking just the part in which v minus k is positive, and then you cut it at 0. Okay?
Okay.
This is the maximum between v minus k and 0. You're essentially taking the higher levels of v. Okay? So let me turn back. Okay. As I was saying, this red part is due to the presence of coefficients and will be used to construct a potential that will preserve, in a sense, certain size properties of the gradient along the iteration. Now, as you can see, in general, controlling a fractional Sobolev seminorm is typical for non-local problems. Okay, just think to the S Laplacian, the SP Laplacian, okay, where there is natural to control a fractional seminorm of your function. No, you just need to test, and what you get is precisely this non-local Caccioppoli type inequality. However, here we are working with a local problem, okay? However, the fact that we are dealing with elder continuous coefficient naturally lead to a non-local Caccioppoli type inequality that is essential, that originates for the intrinsic non-locality of elder continuity, okay? Again, the idea is that elder continuity can be seen as a sort of fractional differentiability, okay? And now it comes, if you want, the more delicate part of the proof, in a sense, because for getting non-local estimates for local problems, we need, in a sense, to delocalize the problem by employing a local decomposition argument that morally resembles the Littlewood-Paley type construction that is made in the dyadic decomposition of Biesov spaces. Okay. What we need actually is to homogenize, okay, the coefficient. I say that the elder continuity must be turned into fractional differentiability. So I need to homogenize the elder continuity of my coefficients with the gain of fractional differentiability for my solutions. Now, atomic decomposition in general is very well behaved in linear problems, but fails to deliver results in the non-local one. Here, the key point is to replace atoms, usual linear atoms that are functions, with solutions of suitable nonlinear equations. And of course, this makes the whole procedure much more involved. And once I have my fractional Caccioppoli inequality, this gives rise to a fractional version of the Giorgio iteration. Okay, remember that thanks to renormalization, all the quantities I have are homogeneous, or at least look homogeneous, so that I can trick iteration.
Excuse me, ma'am.
Tell me.
One thing more which I ask. In previous slide,
Yeah.
you wrote that fractional differentiability.
Yeah.
And if we see the literature, there are many fractional derivative like as Caputo, Riemann. Then can you specify differentiability? Which type of differentiability you explain here?
What I'm explaining is the usual membership of another continuous function to a fractional Sobolev space. In a sense that if you take, this is just a simple exercise that really rely on the definition of elder continuity, you can see that an elder continuous function, let's say C0 alpha, elder continuous, belongs to all fractional Sobolev spaces WSP with S strictly between 0 and alpha, and all finite P. Okay. In this way, you are saying that it's true that my coefficient doesn't have a gradient, but still it has a little bit of derivative, and this will be enough. Okay.
Okay, thank you.
Okay, now, once I have a fractional Caccioppoli type inequality that is again made homogeneous, then I can start iterations. Now, to be more specific, what I do actually control is a sort of averaged version of differential quotient that is essentially a bias of norm, that in turn will allow me to control, by embedding, a fractional Sobolev seminorm. Now, how do I move here? First of all, as you may recall, I need to homogenize the elder continuity of the coefficient with the gain of fractional differentiability for my problem. Okay? So, to do so, I just split my space, you can just think to the unitary ball, in a mesh made of cubes whose size is comparable to modulus of h to the beta 0. Okay, now, graphically, this is what is happening. I have my mesh of very small cubes whose size is proportional to the fractional differentiability gain. And what I do, morally speaking, is I try to decompose, okay, my original function, my v, okay, as a decomposition of nonlinear atoms. What are those nonlinear atoms? Well, my nonlinear atoms are simply solutions to this frozen Dirichlet problem, okay, posed on balls concentric to my cube. Why those are the real nonlinear counterpart of the linear atoms that are originally employed in linear theory? Well, if you recall the theory about classical atoms, they are made of bound functions, and they, in each of their derivative has, the expected decay. Okay. Now, as I said, classical atoms perfectly works for linear problem, but fails to deliver results in the nonlinear ones. What I do is to replace classical atoms with nonlinear ones. My nonlinear atoms are solutions to nonlinear Dirichlet problem. Now, nonlinear Dirichlet problem might be pretty much degenerate. Therefore, how do I recover the decay that I need? Well, I recover it via Caccioppoli inequality. I will have just a decay for one derivative, which will be more than enough for my scopes. Okay. Now, this is the way to control, on the left-hand side, a fractional Sobolev seminorm that, again, comes by delocalizing the problem. Now, using fractional Sobolev embedding, what I do get is a reverse Elder inequality, okay, that now involves my upper truncations of V, my renormalization constants. So this looks pretty much similar to classical reverse Elder inequality, plus a remainder term that comes from the presence of coefficients. Okay. Now, those are constants, the blue part. Okay. Therefore, this inequality, this reverse Elder inequality, is more than enough to start iterations. And at this point, I should highlight the presence of the second main ingredient. That is this general class of nonlinear potentials that were pioneered by Havin and Mazia in the 70s. But at this level of generality, we define this, we introduce them in this paper. Okay. Indeed, as you can see, for proper choices of theta and sigma, we recover classical Riesz potential and the Havin-Mazia-Wolf one. Okay, you can see them in linear theory, the first one, or in nonlinear potential theory at the gradient level. Well, the second one you can see for deriving zero-order potential theory for the non-homogeneous P-Laplace equation. Okay, now, what do we need? To conclude, we need to start iterations. So to start at the Giorgi type iteration that will eventually deliver gradient boundedness. Now, the Giorgi iteration is probably one of the most classical tools in regularity theory. However, very few experts know the way constants deteriorate along iteration. Indeed, if we keep close track of constants in the Giorgi iteration, we may observe that they deteriorate polynomially, okay? So essentially what happens is that if I start with a constant raised to power 1 in my reverse-Elder inequality, I end up with a constant raised to a power larger than 1. This is a polynomial deterioration, not an exponential one, like it happens, for instance, in the expansion of positivity, when you want to prove, for instance, Elder continuity. There, the deterioration is exponential, and this makes it essentially impossible to control constants. While here, there is still hope of controlling constants. Moreover, also the coefficient part deteriorates along iteration. And what it is possible to do using the dyadic decomposition features of potentials, it is possible to reconstruct a nonlinear potentials. They still keeps track of the component of your reverse-Elder inequality coming from the coefficient. Then we can use a covering argument and obtain a quite strange L-infinity energy estimates. Because here, aside from what one classically expects from an L-infinity energy estimates, here we have also an L-infinity norm on the right-hand side, which looks a bit weird, and the nonlinear potential. So we still have two, let's say, characters to take care about. Now, our constraint linking exponent, Elder continuity of the exponent, and ambient dimension implies that this lambda naught is strictly less than 1. And this is good news. This means that we can reabsorb that quantity. Moreover, the mapping properties of nonlinear potentials among function spaces allows us to keep under control this red term by means of by a large power of du, like the LS norm of du for some s quite large. But this is not a problem because if you remember, we already know that the gradient is integrable upon any power. Okay? Now, this essentially allows us to conclude because the fact that our lambda naught was strictly less than 1 allows us to apply Young inequality so that we can separate this L-infinity norm on the right-hand side, putting a small coefficient on front, plus the energy term, which is perfectly fine. Now, the last part goes via a classical iteration lemma due to Giaquinta Giusti, so-called simple but fundamental iteration lemma, that allows us to reabsorb this bit on the right-hand side and to conclude with our L-infinity energy estimates. Of course, now I cheated on lots of details, okay, on lots of them. However, what I wanted to highlight is the possibility of gaining uniform Lipschitz bounds for this class of non-uniformly elliptic problems. Once I know that the gradient is bounded, then non-uniformity becomes immaterial. And therefore, I can, in a sense, trace my problem back to, closer to the uniformly elliptic setting, and therefore applying relatively more standard techniques to prove that the gradient is actually Elder continuous. Now, this method is very general and several applications are possible, and with this I conclude and I thank you for the attention.
Thank you, Cristiana. Does anyone have any questions? If not, I have one question. Cristiana, you mentioned that Giraud was motivated with different kind of applications, for example, in homogenization theory. Do you know, did he deal with applications mainly in linearized elasticity and conductivity, or did he also study applications to higher order equations, for example, fourth order and higher, or only second?
Can you repeat the last question? The last word, sorry.
Do you know, did he only study applications for second order equations like linearized elasticity and conductivity, or did he also study applications to higher order equations such as fourth order and other?
No, he worked mainly on second order. And what he produced is a series of interesting models that in a sense, indeed, aside to give lots of insights towards the general theory for non-autonomous, non-uniformly elliptic models, also give lots of insights on the possible occurrence of Lavrentiev phenomenon and, let's say, what are those class of assumptions that cannot be violated if you want to have well-behaved problems. However, if you want to deal with the higher order problems, I believe that some of these techniques can still be used.
Thank you. Thank you for your answer. Are there any other questions maybe?
I have a problem on the under the fractional framework. Under the fractional framework.
Yeah. Tell me.
I have a problem about the perturbation method. Is this method useful when we deal with no standard growth problem under the fractional framework?
You're thinking about fractional non-autonomous problems?
Yes.
Yes. Okay. So for standard, for the case of let's say uniform ellipticity in fractional setting, you can use these perturbation arguments. If you consider the non-standard one, well, in this case you should be quite careful because the presence of coefficients might, in a sense, perturb also the notion of fractional derivative, in the sense that there you have a heavy object to control, right? And now also the coefficient becomes part of this. So it is quite delicate to handle, but still the backbone of these techniques can work in this framework.
Okay, thank you.
Are there any other questions maybe?
May I also ask one question?
Please.
Thanks. You're naturally talking about partial differential equations. Is there any extension here to SPDEs, to stochastic differential? Could this
stochastic differential equations? Well, I'm not sure because the framework is, I mean, quite far from this, but the hardcore is. The hardcore of this method is robust enough to be adapted to derive to say something about stochastic PDEs. I still haven't tried.
Sure. Thank you. Thanks.
Okay. Any other questions maybe? If not, thank you all for coming and supporting our seminar, and especially Cristiana, to you for giving this very nice first talk. And
thanks a lot.
Thank you.
Thank you, Cristiana. Thanks you all
to you
for coming. We wait for you in the next month.
Bye.
Thank you. Bye.
Bye.
Bye. Bye.
Bye.